Hi everyone. My name is Wihan. I'm a student here, and I'm from the optics student chapter. It's my pleasure to introduce our afternoon keynote speaker, Professor Aydogan Ozcan. He's the Chancellor's Professor and HHMI Professor at UCLA. He's expert in multiple optical subfield. He has numerous awards, too many to list. And what will be interesting for us today is his work in the virtual staining of biomedical samples. So without further ado, please join me in welcoming Professor Ozcan.
Thank you. Well, thank you. Thanks for having me. It's my first time at this conference, so very exciting so far. Today, I'll share with you some of the work that we've been doing on virtual staining of label-free tissue. Before I get into the details, I need to be closer, or probably it's on.
It's
Probably.
there we go.
Let's see. Yeah,
Yeah.
should be working. All right, so my lab is interested in 3 areas of research, one of which is computational microscopy, how to enhance images of microscopes of different kinds. Another area is point-of-care diagnostics, mobile diagnostics, how to convert smartphones, for example, into different kinds of sensors and different kinds of point-of-care devices. And a third area not shown here is optical computing. How can you structure materials, for example, for computing as they interact with light? Today, I'll be sharing with you our work on the use of deep learning for enhancing microscopic imaging, but not for classification of images, segmentation of images. I'm interested in reconstruction of images and transforming contrasts of one type of a microscope into another one. How can we synthesize new contrasts, new kinds of image reconstruction methods? It's a very interesting area, and for this task of image reconstruction, there is arguably one major advantage of using deep learning, and that is, once it's trained, the function approximation power of a network, once it's trained, it's extremely fast and non-iterative to get the result out. And that's actually quite different than the past several decades of research in inverse imaging problems, because most of the ground truth methods in solving an image reconstruction problem has been, by and large, iterative. And they were slow, convergence issues, and all of that. So that's probably one of the biggest advantages of networks. It has its own issues too. I'll cover them in the next few slides. So over the last 7 years or so, we've been applying this to various different types of microscopic imaging methods, starting from, for example, super resolution, taking a low numerical aperture image of a bright field sample, bright field microscope, and mimicking a higher numerical aperture objective lens and improving the resolution of the image using a function approximator that is essentially trained with a high numerical aperture imaging system and taking low NA results and creating super resolution images. For example, you can take a smartphone-based microscope, inexpensive field portable system that attaches to the back of a smartphone. It has all kinds of aberrations and resolution issues, but you can establish a transformation with input coming from a smartphone-based microscope, mimicking diffraction-limited imaging coming from a benchtop system, so that you can actually have inexpensive field portable systems working like more advanced imaging systems. So in all of these and many other ideas, the common theme is solving an inverse problem where we're using the network itself and its learning capabilities as a proxy for solving an inverse problem. In that sense, the ground truth that helped us to train the neural network was coming from a physical understanding of the image formation process. So that's why you can think of this as the first level where we were approximating a physical function. that we knew the ground truth. Maybe it was a slow method, iterative method. And in all of those cases, the network was trying to mimic those known transformations, known physical forward models. But that was probably, arguably, the baseline initial success that helped us think, hey, maybe there is a bigger opportunity ahead of us. And arguably, the biggest opportunity for image reconstruction using a deep neural network is approximating a function that we do not know. So even we might not know if that function can be expressed, can be really attempted in terms of the input-output relationship. So how to approximate functions that we do not know and how to benefit from that power of supervised learning. So this is arguably the biggest, I think, impact that these ideas had for microscopy and image reconstruction, image transformation. Let me give you a more concrete example. Let's take fluorescence microscopic images of specimen, in this case, autofluorescence. So the sample is label-free, no exogenous fluorescence, just everything endogenous, native contrast of, let's say, the specimen. This function that I want to approximate is going to take the input images of that label-free autofluorescence image and create the bright field equivalent of the same specimen, except on top of the modality of the microscopy being different at the input and output, it's also going to be the labeled version of the same specimen. So this is clear that function f is clearly outside of our understanding of light-matter interactions. We cannot really formulate a forward model that's going to take a label-free autofluorescence contrast and tell us how it's supposed to look under bright field microscopy after it's gone through a labeling process. Microscopy modality is changing, and the sample itself is also changing. So that's kind of a very difficult transformation. But with image data, you can have an attempt at approximating that kind of a function, f. So you may be wondering, hey, this is so interesting, so peculiar, so who cares about a function like that? Well, that's exactly the topic of my presentation today, because that function f would be very valuable for histology, for creating synthetic contrast, synthetic labels, what we call as virtual staining. Literally for the last approximately 2 centuries, we stain tissue taken from a biopsy, let's say, because if you thin section a tissue section, let's say a few microns thick, it doesn't have any contrast under bright field microscopy. It looks like glass. That's the reason why for the last 2 literally centuries, we've been staining tissue samples with different kinds of dyes, chromophores or fluorophores, so that we bring contrast to the microstructure of tissue. And that process, the histochemical staining process, depends on the stain, can take a couple of hours to a day, tedious and expensive, and sometimes not so well repeatable. So the previous function that I just described, f, if you could learn that, you could actually bypass this histochemical staining process and have a neural network trained with respect to the ground truth coming from a histology lab, where the inputs will be label-free autofluorescence signatures of the same samples before the staining process. Which means you can stop the workflow here, take the thin section, a few microns thick section of the label-free tissue, and look at the contrast coming from endogenous fluorescence at the single pixel level. That's the a soup of fluorophores that give us the contrast and beautiful diffraction-limited image to be transformed into an image that, from the perspective of the pathologist, you cannot tell the difference if it is histochemically stained or virtually stained. So that's the gist of virtual staining, if I could approximate that function f. So, oh, that's not mine. So how do you do that? So there are various different ways of creating synthetic contrast through virtual staining. One of our favorite frameworks is conditioned generative adversarial networks. How many of you used a GAN before for your research? So this is actually a structure where it's a framework where two different convolutional neural networks fight with each other. You can think of this one as the painter. That is the virtual stainer. That's what I want to retain at the end of this learning process. So it takes beautiful diffraction-limited images of label-free tissue. So this got a large NA, as close to as possible to 1, and it has beautiful microscopic features at almost the nanoscale. And its goal here is to create the virtually stained image, which is going to have some structural loss terms, which will give us basically a minimum structural loss compared to the ground truth coming from the histology lab. So this is a process where you start with label-free samples, you capture the autofluorescence image, and then the whole process goes through the histology for us to generate the ground truth so that we can actually condition the generator to be faithful to the micro and nanostructure of the ground truth labeling. The function of the discriminator is to help learning of the generator. It tells if it can separate, for example, virtually stained images from histochemically stained images and vice versa. And it helps learning of the generator. And at the end of the day, if you train this well, the discriminator is going to be failing 50% of the time, which means then you have a beautiful generator that is faithful to the ground truth structure, and also it fools the best AI in terms of telling which one is virtually, which one is chemically stained. After this learning process, game theoretic approach, we take the generator and say, hey, this is good. It's learned what it's supposed to do, and we apply new samples, new patient specimen, never seen before, to test how well the generator generalized to new specimen. So everything that I'll share with you in the next several slides, these are blind testing examples from new patients never seen before. This kind of a framework works for various different tissue stain combinations, not just for H&E. H&E is a very common form of stain used in histology. More than 95% of human tissue is stained with H&E. This is relatively fast. It takes about 2 hours for a histechnologist to create an H&E image. That's why it's cheap. In terms of dollar volume, it's about 50% of the market. So H&E is 50% of the market, despite the fact that it's 95% in case volume. So what you see here is a DAPI contrast, DAPI filter autofluorescence. That doesn't mean we're using external fluorophores. It's label-free. I'm just looking at autofluorescence processes through an existing filter set. It's contrast enhanced for your eye. This is just for your eye, to show you that we have beautiful texture there that is contained in this image. This is the only thing that you need for virtual staining. This is the ground truth coming from histology lab after approximately 2 hours of human histechnologist time. So it's a beautiful match, and of course, this is less than a minute for a whole slide image if you have enough GPUs. It doesn't only work for these simple stains, it also works for special stains like, in this case, Jones silver stain. This one is, the ground truth here is, this is kidney tissue. It takes about 3 hours. It's more tedious. The human histechnologist would typically spend quite a bit of time under the microscope to make sure the process is evolving right for the histochemical staining to kind of succeed. That's why this is approximately 10 times more expensive, at least at UCLA, per patient. And the same idea applies. Label-free contrast, microscopic images taken with a digital scanner, network output, nicely matching what comes out of histology after a couple of hours of tedious staining process. And some of the examples are shown here. This is a different type of a stain, Mason's trichome. Also fairly laborious, approximately also 3 hours, and about, again, 10 times more expensive. It's also part of the special stain category. And the contrast from DAPI with label-free samples are shown here. Inference of the network is shown there, which is compared to histology on the far right, made by a human histechnologist. This kind of a framework can also get to even more advanced stains. In this case, we're looking at immunohistochemical staining. This is antibody antigen specific stain, and it takes about 24 hours. So this is really a fairly expensive and tedious stain to perform. Literally with the incubation and everything, you're looking at an overnight stain. We're looking at, in this case, HER2 expression, which is a key biomarker for breast cancer patients, which means we're looking at these receptors and their density, expression density. For some patients, this is a HER2 3+ category, which means it's overexpressed. And depending on the patient history, this will have a different therapy. This is HER2 0. So that's kind of like not showing any contrast with brown color, which is expressing this HER2 protein density. In this case, we were using 4 different autofluorescents because this is a more difficult stain. It had, in this case, as I said, the ground truth is about 24 hours. And that's why we were using, again, label-free contrast, but 4 different types of filter set to give us different texture. This is not a pixel-to-pixel mapping. This is a texture-to-texture mapping because for something like this, which is at the nanoscale, we don't have the resolution in autofluorescence to reveal where exactly that antibody is binding. It's actually understanding the neighborhood of where that expression is happening. So in this example, inference time is about the same. So it's literally saving here 24 hours of staining, chemical staining with toxic chemicals. So these were examples left and right of how virtual staining results compare from the perspective of images against the ground truth coming from histology. And we have quantified structural similarity index, PSNR, color distances, all kinds of engineering matrix that you can have to understand the equivalence, statistical equivalence between the 2 sets of images. But that's not sufficient because at the end of the day, the consumption of these images will be by board-certified pathologists. That's why we had to create our own Turing test for pathologists. We gave a group of board-certified pathologists in a blinded manner several images of virtual staining and histochemical staining for them to quantify the quality of nuclear detail, extracellular fibrosis, etc. And so many of these kinds of tables were created to show that there's statistically no difference between the quality that they perceive from our images versus standard histology images, except we're slightly better. Same conclusion applies to, can they diagnose the patient's condition accurately with our images as opposed to standard histology images? The same conclusion in a blinded manner, they were able to reach the same conclusions in their diagnosis with our images, meaning that it's not just looking cool, nice images from the perspective of engineering. They're also preserving diagnostic features that are within the tissue. But there are so many important advantages of virtual staining. It's not just matching the quality of histochemical staining. It's actually improving over it in many ways. First, we're standardizing the quality of staining. Look at, for example, this panel here. This is UCLA Health, H&E, the most simple to perform stain. And you see quite a bit of variation here. That's human-to-human variation. And this is happening everywhere. And it's bad for diagnosticians, human diagnosticians. It's also bad for downstream AI. So you may be overfitting to some of these peculiar styles of staining, which is not good if you want to do, let's say, tumor margin detection or staging of cancer using AI. That's why standardizing the quality of the images, style of images, is very important for both AI and for human diagnosticians. Arguably, the biggest advantage of virtual staining is actually multiplexing, which means from a single cross-section of label-free autofluorescence, you can have a panel of stains that are nanoscopically registered. That's very exciting because if you think of a panel of stains required from the patient, think of, for example, organ transplant rejection. It starts with H&E and soon it goes to special stains depending on the condition of the patient. You will have many stains generated, but they're coming from different parts of the tissue. So a lot of times we deplete tissue, we complete the biopsy processing because there's no more tissue left. We bring the patient back for a secondary biopsy. Most of that is because of the destructive nature of these multiplex stains that we need. That's not necessary for virtual staining because from a single cross-section, you can have a panel of stains And you can multiplex them because now the diagnostician can switch from one to the next one with the same exact identical cross-section at a nanoscale because they're coming from the same common image field of view. So these were biopsy samples that we virtually stained. The same framework also applies for autopsy samples, in fact, much better. For autopsy samples, the ground truth is shaky, meaning that because of delayed fixation of the tissue and the large area of autopsy samples, there's a common problem. That is autolysis of tissue, and that unfortunately makes the traditional chemical staining fail. It's a known problem. Look at this, for example. This is a COVID patient, autopsy sample. The traditional histology completely failed. Nuclear features are missing there. That's because it denatured. You cannot stain it. There's nothing that you can do. You cannot recover that autopsy area. Virtual staining, it shows that it's resilient. The texture of autofluorescence at different bands, at different filters, actually preserves, despite degradation of tissue, the morphology that you can transform. It's a very interesting conclusion here. You're better than the ground truth. That's kind of like oxymoron for AI, but you are better than the ground truth. In fact, for this training, we had to exclude a lot of the regions manually. That's why the garbage of autopsy sample failure did not enter our training process. That's why this didn't influence us, and we can still get perfect, near perfect virtual staining despite these autolytic regions of tissue. The same conclusion also applies for immunohistochemical staining. Approximately 30% of IHC staining, immunohistochemical staining, fails because of human error, because of antibodies degrading, you name it. So in that sense, you're, again, better than the ground truth because we filter out those garbage coming from histology lab, knowing the patient's health record, which means during training, you train with the best. And therefore, if you make a perfect comparison with the histology lab, you're actually better than them. This is another recent work that we have shown you can do virtual staining in a multiplex manner for also bringing an additional contrast. Here, we're looking at amyloid deposits in tissue samples that are virtually stained. For amyloidosis, one of the problems is delayed diagnosis because most diagnosticians do not look for amyloid deposits within tissue. That's why a typical patient would be diagnosed maybe 3 years delayed compared to the onset of the symptoms. And the reason for that is looking for those amyloid deposits is a tedious process. You have to first do a staining of the tissue, Congo red. It looks like this. Then the diagnostician would manually examine these thin sections under a polarization microscope because amyloid deposits are birefringent and they rotate the polarization. That's why under a polarization microscope, they look for these apple green signatures. What we've shown here is that autofluorescence carries information that is sufficient for you to switch to Congo red and the birefringence at the same time, which means you can now do virtual Congo red, virtual staining, and virtual birefringence. So that's actually fairly interesting because in digital pathology workflow, there is no digital pathology. The good thing is this, in digital pathology workflow, there is no FDA-cleared polarization scanner. As a result, this apple green birefringence examination is a tedious, mechanical, manual process done by pathologists. They hate this. And guess what? Sometimes they don't have the proper microscope for it or training for it. That's why we've shown that you don't need a polarization microscope, just like you don't need a stainer or a chemical staining process. You just also don't need a polarization microscope, which doesn't exist in the FDA-cleared form. That's why it's a manual process. Autofluorescence is very interestingly powerful. It also lets you understand birefringence processes along with the staining process. If you look at these images here, can you go back to the same thing? My clicker is not working. So So if you go to the next slide, you can see that from autofluorescence contrast, we were able to, at the whole slide level, get the staining done and birefringence on the top of staining performed. Here we're using mathematically an interesting construct which conditions this virtual staining network to reveal either congruent or virtual birefringence by a digital staining matrix. One state reveals congruent, bright field equivalent. One state reveals polarization microscopy equivalent. You can play with these digital staining matrices. It's very fun. You can condition them with some numbers and then create hybrid numbers to synthetically generate contrast, kind of like virtual alchemy. So these were coming from fluorescence, autofluorescence contrast. Arguably, that's my favorite contrast for virtual staining because it's molecularly specific. If the problem is hard, like for example, immunohistochemical staining, I just switch a few different filters, FITC, Texas Red, let's say, DAPI, Sci5. Then you get all what you need from alternative channels and you can do a beautiful virtual staining, even for molecularly specific stains. But that's not the only label-free microscopic contrast. Another favorite of mine is actually holography, quantitative phase imaging. How many of you are using QPI or a form of phase contrast microscopy for your work? You can use phase contrast for virtual staining. It's a very powerful means. Basically, it is looking at the refractive index of tissue as a native contrast. Refractive index at the subcellular level is a distribution that is an endogenous contrast, a biomarker of tissue. You can use that. In fact, this transformation here, F function, is a completely different, peculiar, and out-of-reach type of a forward model. Phase contrast in the form of holography is spatially and temporally coherent, and bright field of the labeled version is spatially and temporally incoherent. So this F function is beyond our understanding. So it's really the power of supervised learning. Otherwise, I wouldn't be able to relate these two quantities. They're physically apples and oranges. We call this phase stain. It's quantitative phase, refractive index contrast, phase contrast, all the derivatives of these, where you use, in this case, optical path length or phase signature at the input, a similar architecture with a similar conditioned GAN framework, trained with histology images coming from a lab, learning the transformation from quantitative phase imaging into bright field equivalent of those. So that's why the grayscale images, the color bar here, reflects phase. That's quantitative. that's really telling you at that wavelength how much the tissue was delaying the light propagation. That's an endogenous contrast, giving you beautiful H&E-like images for skin. It also works beautifully well for more exotic stains. This is a different Jones-Silver stain and Mason's trichome for liver and kidney tissue from, again, endogenous contrast coming from QPI, quantitative phase imaging. In a recent work, we've also used another contrast mechanism, label-free. And this one is reflectance confocal microscopy, RCM. How many of you have used reflectance confocal microscopy? Great. Wow, fantastic. It is an FDA-cleared device for dermatopathology. So this device is FDA-cleared. Some clinics would use it to decide if they should biopsy you or not for skin lesions. So it can, without taking a biopsy out, gently, touching on the skin, it can reach up to perhaps 100 microns, less than that, but up to 100 microns, and capture beautiful label-free contrast grayscale of reflectance confocal microscopy. It gives you a stack of these images. Arguably, one of the biggest limitations of RCM is pathologists don't know this contrast. So that's why they don't like it. That's probably one of the barriers for its wide adoption. What we've shown is that you can take a stack of these images and create synthetic contrast coming from these RCM grayscale images to do biopsy-free in vivo H&E. In the next one, I'm sharing with you a movie of how it's operating on a new patient never seen before. This is essentially, let's say, the new patient's arm. You get these RCM images, and with a running average, as you go into deeper and deeper into tissue, you're creating H&E images coming from a stack of RCM images that are entering the input of the network. This is 3D to 3D, basically, which means the inputs are, in this case, 3D stack of images with some delta Z that's small. What I'm showing on the right is actually portability of this model, which means this virtual staining model was trained with a benchtop FDA-cleared RCM, reflective confocal microscopy. But for the first time, I'm testing it on a new patient with a handheld version of the same system, except optics is different. It's the same contrast, but the optical instrumentation here is slightly different, miniaturized in some sense. For the first time, without any transfer learning, it's actually plug-and-play ready. This is unusual. Most virtual staining systems, if you change the microscope or the numerical aperture or the CCD, whatever you use like CMOS, you have to do transfer learning to get the best out of your model. In this case, the resilience of the network for RCM from benchtop to portable is most likely because the inputs were three-dimensional. We were having a 3D cube at the input that made us more resilient because it was actually looking at a volumetric information of RCM cross-sections as opposed to a single layer. So I want to come back to this slide, which is arguably the biggest advantages of virtual staining. From a single cross-section multiplex staining, preserving tissue, giving you for the first time a contrast that from one stain to the next stain to the next stain is matched within the structure of the tissue, nanoscopically matching. But that also highlights a very exciting stepping stone for us. If from a single cross-section, I can go to stain A, stain B, and stain C, let's say, they're perfectly registered, then I can also hop from stain A to stain B and any stain. That means I can do stain-to-stain transformations, which means if I'm too late or if somehow the workflow gives me a very quick H&E, I can take H&E through these kinds of multiplex virtual staining, convert the H&E to anything that you want. That's a very important and exciting opportunity because we have a lot of H&E stored in our databases as part of our hospitals. And that means now we can ask the question, hey, for that patient H&E, how would it look like if I were to get on the same cross-section an IHC with a certain biomarker, et cetera. So this kind of a scheme would be also very useful, especially if an initial H&E is quick and part of the workflow. A good example of this that we've demonstrated is for some organ transplant patients, we took their H&E images and transformed them into 3 special stains that are required to understand their condition. In this case, PAS, Mason's trichome, and Jones-Silver stain. The clinical workflow today, because of different reasons, insurance reasons, you have to start with the H&E. You cannot get these immediately. The diagnostician has to look at this first, but that takes time, during which the patient must be hospitalized depending on the condition. So if it's a Friday, you're looking at a few days of hospitalization before these come out based on the H&E report. What we've shown here is that with different cases, we gave them, the diagnosticians, only H&E and asked them to diagnose the condition versus a quick H&E and virtually stained panel from stain-to-stain transformations, taking the H&E and giving you the panel that you want on demand, kind of bypassing the waiting time for H&E plus the special stains to come. And we've shown that the diagnosticians improve their diagnostic accuracy on the patient specimen if we were to augment their decisions with stain-to-stain transformations coming from a quick H&E and then going to special stains transforming the H&E into different types of stains. And this is enabled completely by virtual staining, label-free virtual staining, and its ability to go to stain A, stain B, stain C, so that I can establish transformations between any 2 combination of stains. To sum up, virtual staining saves time, cost, and it preserves tissue. It will eliminate secondary biopsies because tissue staining is a destructive process. This is especially important for small tissue specimen like that is taken from, let's say, an organ transplant patient, those a couple of millimeter thick needle core biopsies would be very precious for destructive staining to happen. This also standardizes the staining quality, and arguably this is also a green technology. So something that is based on AI, GPU, all kinds of electricity costs coming from your GPU clusters. Despite all of that, all that carbon footprint, this is actually a green technology because most stains today are toxic. Because of tissue staining, every year we're wasting a couple of million gallons of water. And that's going to be unnecessary by and large. That's why that will be offsetting the carbon footprint of all kinds of GPUs that you use for training and inference stage of this technology. This is also not an academic exercise. It's actually a company that I co-founded in 2019. So this is a startup that we established from our lab. It's called Pictor Labs. Pictor in Latin means painter. So we're painting microstructure of tissue at Pictor Labs. This is how I started my VC pitches during the pandemic. So far, we've raised about $50 million. And the comparison of what we want to achieve is highlighted here very well. Today's pathology is like the blockbuster. If you want to see a patient's specimen with one contrast, with another contrast, it's very much like getting those DVDs and playing them with your microscope. But if we could have virtual staining, it's going to be like Netflix. The diagnostician on demand will be able to access different content and switch between different stains that are necessary for diagnostic purposes. And I'll show you this movie from Pictor Labs. It's a commercial model, which is showing you the power of multiplexing. This is a whole slide image of cell carcinoma. And you start with H&E, virtual staining. You can zoom in, beautiful contrast. And then on top of this, you can bring an IHC. In this case, it's going to be pan-CK. This, again, takes about 24 hours to get a good pan-CK. And somewhere else, if you need to switch the contrast, you can go back to a special stain. And soon you're going to see Mason's trichome on different parts of the sample being superimposed to these different stains. So this was the power of supervised learning, in the sense that it all started with approximating unknown functions. Arguably, that's the biggest advantage of supervised learning. It helps us look at processes that remain outside of our understanding from the perspective of inverse imaging problems. And for this, supervised learning has a lot of interesting things to offer. However, it also has quite a bit of problems. First of all, for something like this, you need to clean your data. You need to pre-process your data. I haven't talked about it as much, but there's a lot of domain expertise that is required for training one of these models. And that's how we are better than the ground truth, because we reject garbage of human staining results. Sometimes it's 30% of the time for immunohistochemical stains. That is why you need to do a lot of cleaning and pre-processing of data with pathologists in the loop. But that's a one-time effort. Once you're done, you generate some beautiful stainer that stays with you. For that, you also need diverse training, high-quality training. And that's another problem. You need a lot of data. And of course, what's learned is opaque. Well, it's the chicken and egg, right? So if this function is opaque, that's what is learned in this case. So it's going to be remaining opaque as well. And you can ask me a lot of questions about hallucinations. This is my favorite topic. So I'll leave it to discussion. But of course, there's a concern about the use of these kinds of technologies for FDA-regulated primary diagnosis and et cetera, right? So that's why you got to be careful about that and how you frame it, how you use it, et cetera. So those are all the issues that we are dealing at Pictor Labs, trying to kind of commercialize it and go through the FDA and everything. By the way, this is my conflict of interest disclosure in the sense that I'm a co-founder of Pictor Labs. So now I want to switch gears and tell you a little bit more about how some of those problems with supervised learning, all these red negative things about supervised learning, despite what it enables is fascinating, how can we mitigate some of those in general? And for that, I'd like to see if we can use physics as a regularizer. So can I use basically physical laws to help the learning of a neural network for solving an inverse problem? And that's something that is quite interesting because perhaps it can address all of these issues with supervised learning. So for this, I'll share with you the story of Gedankennet. How many of you know what Gedanken means? Yeah, in German, it means thought. It's a frame that is popularized by anyone? The famous physicist? Einstein. So thought experiments in quantum electrodynamics is a term that he framed as Gedanken experiments. And that's why we call this Gedankennet. So the story of Gedankennet is as follows. Think of a form of AI in Jupiter that has never been to Earth. It doesn't know anything about humans. It doesn't have any knowledge about our tissue samples, how we look, etc. It doesn't have any microscope of any kind or any sample of any kind. So, but it's tasked with reconstructing holograms or generating quantitative phase images, just like the contrast that I use for virtual staining, the phase stain, the phase contrast that I've shown you. So the task that this AI in Jupiter is given is to reconstruct in a self-supervised manner to teach itself how to reconstruct a hologram of a sample, like let's say a tissue sample. The only thing that it knows, despite not knowing where Earth is, what kind of people live on Earth and how our tissue looks, etc., nothing of that nature, no experiment, no data, no sample, no prior information. The only thing that it knows is it knows the Maxwell's equations. So it knows the general wave propagation. Wave equation is driven from Maxwell's equation. So the only thing that it knows is some physics. Okay? And waves propagate the same way in Jupiter and Earth, so it's a universal law. So it's going to take the wave equation and use it as a regularizer to teach itself some physics. And then once it's trained itself on how to reconstruct a hologram, we're going to send that AI to Earth and say, hey, I'm going to give you an experimental result of a hologram, and I want to see how it looks with the phase contrast of the tissue sample. So zero-shot learning, which means you must be successful first time after you trained yourself without any data, without any prior information on Earth. This is called self-supervised learning with physics in mind. The only thing that it knows is a Gedanken framework, thought framework of experiments following physics. So here is how it approaches this problem. So let's say you pick up your favorite function approximator. It goes inside this Gedankennet black box, a form of convolutional neural net or fully connected or a combination of fully connected and convolutional blocks, something that you need to train, okay? It's a universal function approximator. What it does is very simple. Since it doesn't know anything about human samples, how we look, it's going to hallucinate garbage. So it's going to imagine different kinds of features randomly. And any two of these features will form a complex field, like a wave. Without knowing what a wave is, you can have the amplitude and phase information of a wave, electromagnetic wave, represented with some garbage. No resemblance to tissue or any kind of features. Okay, I have a wave that I hallucinated through a Gedanken thought process. Then the only way that he is or she is training this block here, reconstruction block, is relying on consistency of physics. That's very powerful, which means you don't have to look at there, but just look at my hand. If I take this clicker and drop it to the floor, It will drop at a certain time on the floor. And if I repeat it again, a second later, it's going to repeat exactly the same trajectory, the same exact path. Physics is repeatable. So AI Gedankennet is going to constantly repeat experiments in a thought manner and check the consistency of its experiments, which means at the first red block here, it's going to take a garbage field, optical field, and drop the clicker on the floor, which means it's going to forward propagate the field with a certain known amount. This is kind of dropping the clicker first experiment. Wave is propagated. Okay, if you propagate a wave based on the wave equation, Maxwell's equations, you get a certain intensity distribution. That is kind of what you're going to be measuring. That's my input. That's a hologram. It goes through this black box of image reconstruction module, not trained yet, garbage in, garbage out. So it's not doing its job yet because it's the early phases of self-supervised Gedankennet-based training. However, the powerful thing is this. If Gedankennet repeats the experiment a second time and repeats exactly the same wave propagation, this intensity pattern and that intensity pattern must match because physics is repeatable. So the only loss that is feeding this learning process of all those millions of parameters of that Gedankennet is consistency of physics. Wave propagation, if I repeat it twice, it must exactly get the same distribution. If not, that is an error. And that error must be corrected. That's the entire logic of Gedankennet. Repeats experiments 1,000,000 times until the coefficients of this Gedankennet are fine-tuned. Then, well, no experiment, no hardware, no data, no prior assumption about tissue samples. After a while, it gets bored because it doesn't update as much and says, okay, I'm converged. Probably I understood wave equation now. Then I send the Gedankennet to Earth, and for the first time give some holograms of tissue sample coming from actual experimental quantitative phase imaging microscopes. What you see here is zero-shot learning, reconstructing, for example, salivary gland, prostate tissue, lung tissue, pap smear, first time from their holograms, revealing amplitude and phase information of that thin section of tissue with no experimental data. In fact, the counterintuitive part is this, not self-supervised learning and approximating the wave equation. No, more than that, it beats supervised learning. Which means if you were to take another form of network, same architecture, and give a lot of data coming from the same hardware, and teach in a supervised manner how to do reconstruction, you do poor external generalization, which means if I change the tissue sample from prostate to, let's say, lung, vice versa, you still can reconstruct it, but with some degradation. Gedankennet doesn't care. It actually beats supervised learning in external generalization with new hardware, with new types of microscopes, with new types of tissue samples. Because every hardware, every microscope, every type of tissue, specimen type is specific. So you're overfitting to some degree to the type of the object, to type of tissue, organ, or the hardware. That overfitting penalizes external generalization capabilities of AI. If you regularize everything with physics, it's universal. And that's why it has better external generalization. In fact, if you purposely try to mislead Gedankennet, it doesn't hallucinate garbage. It hallucinates within the boundaries of physics. It's very powerful. Here's an experiment. You take Gedankennet that is trained through thought experiments and purposely give defocused holograms. I'm cheating and I'm giving something that is defocused in terms of measurement. It's at a different plane. It outputs a certain reconstruction as a function of different defocus. And it's incorrect. That's why this correlation constant is reducing. However, guess what? If I were to take this reconstruction of Gedankennet and forward propagate it based on the wave equation. By the defocus amount, it's giving you actually a very good reconstruction. That means whatever it's doing when it's giving you incorrect result is also compatible with Maxwell's equations and the wave equation. It doesn't hallucinate. It gives you a solution that is physics compatible. And this way you can actually train different kinds of Gedanken nets to do autofocusing and phase retrieval at the same time. So you can actually build more complex inference processes for doing holography and quantitative phase imaging. So this was a good example of how physics was used as a regularizer for training AI to be more resilient to have external generalization. Key features here: no experiment, no experimental data, no prior knowledge about human samples, nothing, but purely based on the wave equation and understanding of basically Maxwell's equations. You can also flip this coin. I don't have time for this, but AI can also help physics get smarter at what it can design. So there's a very exciting framework where you can use deep learning principles and optimization framework of AI to construct materials that can compute for a given task. We call these diffractive processors, diffractive deep networks, where AI is helping the physics of light-matter interaction to find solutions for different kinds of tasks. In general, this is a framework where you can synthesize spatially varying point spread functions. If you tell me any arbitrary set of spatially varying complex valued or incoherent point spread function, this kind of a framework with the help of AI can give you a beautiful approximation for that. How can you use that? Well, you can create smart microscopes that can actually compress information, that can recognize information, that can be class specific. It can actually erase everything that is boring and only image target classes of objects. Let's say you're only looking for cell division event. It can only image cell division, ignore everything else. So it will help you eliminate a lot of data that is unnecessarily captured. So these are essentially possible with structured materials where AI this time is helping physics. So that's my last slide. Thank you very much for having me and look forward to our discussions.
A great talk. Given your last comment, one thing that came up in our Bess's keynote was just the challenge that known optically is a solution for scattered deep imaging. Have you thought about getting into that, trying to model scattered light and try to understand how to go deeper using deep learning?
Yeah, so great. I have this slide with me. Okay. Yes, we have. I want to open another presentation very quickly, if you don't mind. Just to look at this one. I hope one has it. Yeah, sorry. Yeah. So the question was related to the last part. It's opening. Yeah, it is working. Yeah, cool. So one thing that is related that we have done is to solve for scattering in an all-optical manner. So I'll just point you to the paper and describe what we've done on it. Right here. Okay. Oops. So you can actually treat a diffractive volume like a trainable system and optimize the features within a diffractive volume to solve for an inverse problem. In this example, let's say you have an object that is unknown and it's constantly changing. And unfortunately, in front of it, there is a diffuser that is also constantly changing and in an unknown way. So what we've shown in this work is you can take a diffractive material that is composed of several layers that are cascaded, maybe with 10 lambda, 10 wavelengths in between. But every part of that diffractive layer, next layer and the next layer, it's actually trainable. You can fabricate things like that by lithography. Trainable means the thickness of each layer has a topology. Let's say 50,000 variables here, another 50,000 variables here. Let's say you have 3-4 layers, 0.1, 0.2 million parameters built in there. During the learning phase, I show lots of examples of arbitrary objects and random diffusers. And I'm penalizing here not a digital network. I'm penalizing the physical parameters of a diffractive processor. Think of the diffractive processor as a superset to your microscope objective lens. Just like an objective lens, this is going to be built in, fabricated, and then be deployed there as a physical image reconstruction engine. These are optimized to stabilize the image despite the presence of unknown random scattering and unknown objects. It actually works pretty well. Intuitively, you can think of it like a 3D specialized filter that you're engraving within material that is statistically taking the modes here and transferring the most useful modes to the output despite the presence of the random scattering. And then after you're done with your training, you fabricate these layers and show new examples of diffusers and new examples of unknown objects. It must generalize to never seen objects and never seen diffusers. That's actually working. The more difficult the problem is, of course, we sacrifice resolution here. So there's actually a beautiful physical insight here. And if you look at the phase profiles of what you learned there, it's actually fascinating. It converges to a micro lens array that is surrounded by a phase code that acts like a filter, noise filter. So those kinds of ideas we're exploring, and you can actually make this more challenging by putting here multiple diffusers, kind of like model a tissue in 3D. This was done for a single scattering plane.
Yes, thank you for your talk. This is Nicolas van der Voort. I'm over here from the SVI Huygens. In the second slide, your introduction slide, you showed that you can train an AI network on stat data to reconstruct stat data from confocal data. And I think this was part of your introduction, not necessarily your own work, correct?
No, it's our work.
Our work, okay.
Yes, so it's Nature Methods in 2020.
Right. So how do you know that your reconstruction is the correct reconstruction?
Because we train it with a STED microscope, so that therefore we have access to the ground truth.
Well, you don't really, because you can also have another object from your STED microscope that would give the same confocal image. You can't tell them apart, could you?
So no, so the same objects are imaged on the same system with a confocal and then a STED microscope. And some of those objects are fabricated by us. So we also know them due to fabrication, due to particle size. So therefore, they are registered during training and blind testing as well. And by looking at the spatial frequencies of the ground truth that is registered to the same field of view, I can understand both the features in space and the spatial frequency features that I'm trying to mimic. So it's basically doing a frequency extrapolation based on known observations.
Can you then also comment on, you mentioned already, the transfer training problem?
Transfer learning problem?
Yes.
Yeah, so let's say I trained with, let's say I took a 0.4 numerical aperture NA, and I'm trying to train it against a, let's say, 0.8 numerical aperture system.
I was talking more about, let's say, biological variability. I get the signal. We have to cut this discussion
Transfer
short.
learning applies to biological variability or hardware variability or combinations. Whenever your testing deviates, either from the perspective of the data distribution of the samples or the noise of how you're sampling it, or pixel size at the CMOS or numerical aperture, or the microscope manufacturer. In any of those, there are unknown variables, including unknown data distribution of the new type of sample, or the noise sensor, CMOS being slightly different, with different noise statistic, with different pixel size. All of these would fail the network if they are above a certain range, empirically to be tested. And the best is for you to, when you start actually getting a new type of a microscope or a new type of a specimen, to do some blind testing, through which you can also use your failures as a way to train your network with limited data. We've shown that it becomes very efficient. You don't have to start from scratch.
We had one question from Chad. Yeah, it was a great talk, first of all. For the label-free staining, how would you generalize the model that you have? Is it to different microscopes or objectives or even different types of tissue? Would fine-tuning be needed?
Yeah, so for every tissue stain combination, there's a new network. Therefore, everything that I've shown you in terms of virtual staining was tissue stain specific. And that means, but that's, for pathology, that's the norm, right? There's no unknown in pathology workflow. I know exactly which organ it is and what stain you want. That's why we have models, very much like there are protocols that humans follow when it comes to the lab. It's the same thing. You pull up a menu of different pre-trained models and apply it to the specific tissue stain combination. In terms of device-to-device variability, microscope-to-microscope variability, if these are FDA-cleared digital pathologist scanners, part of the clinical workflow, let's say Philips, Zeiss, Leica, whatever you have minimal variability. We've tested that with several different manufacturers. A model trained with one works beautifully well on the other one, because these are really fairly expensive and diffraction limited, beautiful microscopes that are maintained well, right? So they're part of the FDA cleared pathology workflow. If you go to a less expensive and perhaps aberrated microscope, you can have issues, and that's true. But from the perspective of high-end microscopes, we haven't seen noticeable differences. But why should I give away my performance, even if it's not noticeable to me? That's why if you have a certain microscope in your digital pathology workflow, I should have a model that's specifically trained for that. That's the best.